So we understand DFT in terms of its formulas. Okay, we can compute the DFTs, we can compute the inverse DFTs. I briefly alluded to in the last lecture that DFT has a connection to DTFT. But now what we want to do is really understand how is DFT related to DTFT. So that we can try to make some sense of DFT and not just treat it as a bunch of formulas. So for that, again, we'll just say that we are given a length n signal, and this length n either comes because the signal is length n or you have zero padded, and we compute its DFT x of k, which is the same formula, xn e to the minus j 2 pi k over capital N times little n, and we are going to evaluate it for n numbers. So this is DFT. Now to relate DFT to DTFT, let's look at what will be the DTFT of xn. So we know that formula also. It's x of e to the little j, x of e to the j little omega. That is equal to n from minus infinity to infinity, x of n e to the minus j omega n. Now, we are relating DFT to DTFT. In this case, we are saying we are only focusing on signals which are finite duration, and without loss of generality, we are going to say they are starting at n equal to 0. So of course, then this summation only needs to start at n equal to 0 because everything is 0 before that. And it only needs to go up to n minus 1 because everything is 0 after that. So it's xn e to the minus j omega n. So now we can compare the two formulas. So if we compare the formulas, both the summations, n from 0 to n minus 1, we have little xn, and then we have a complex exponential, but the difference is that in DFT, we have instead of little omega, we have 2 pi k over n. So what this says is that the DFT x of k, the kth value of my DFT, is nothing but my DTFT sampled at 2 pi k over capital N. Okay. All you are doing, because remember little omega, right? Little omega goes from minus infinity to infinity in the discrete time Fourier transform world. And what this is saying is that DFT is nothing but taking n samples of the DTFT. So the information it is conveying to you is samples of your DTFT. And where are the samples going from? So for k equal to 0, this means you are sampling at little omega equal to 0. And for k equals n minus 1, which is the last DFT point that you compute, you are sampling at little omega equal to 2 pi n minus 1 over capital N. So if I solve that, that's 2 pi minus 2 pi over n. Okay. And what are the other samples? Of course, the other sample is k equal to 1. That's 2 pi over n. K equal to 2. That's 4 pi over n. And keeps going till you reach the end. So what DFT is doing is effectively looking at your little omega axis. Your little omega axis, your frequencies of your discrete time signal. They of course go from -infinity to infinity. Right? But what DFT does is it looks at the frequencies from 0 to 2 pi, right? And it divides that equally into, it effectively uniformly samples the interval from 0 to 2 pi. It's just like the sampling of a time domain signal, but now you are doing sampling in the frequencies of the signal. So the first point it samples is 0, the second point it samples is 2 pi over capital N, the next point is 4 pi over capital N, and it keeps on going till the last point is 2 pi minus 2 pi over N. Right? So the gap between any two samples is always 2 pi over N. So that is the interpretation, at least when you look at it from the perspective of just DFT versus DTFT. You can't compute DTFT because it's a function of a continuous variable. It can't be computed inside a digital system. And what DFT is effectively doing is sampling your DTFT at points so that you still recover the original signal. Okay? The fact that inverse DFT formula works, that is saying that these many samples, n samples of your DTFT are enough to recover your original signal. Let me repeat that again. In general, if you are given x of e to the j omega, and you want to find out what is the signal that this Fourier transform belongs to, right? You compute the whole integration, right? So to go from this to xn, you do xn equal to 1 over 2 pi minus pi to pi x of e to the j omega e to the minus j omega and d omega, e to the plus j omega and d omega, right? So you need the DTFT for all little omega from minus pi to pi, right? But what have we learned so far? The first fact is that DFT corresponds to n samples of the DTFT taken at little omega k equal to 2 pi k over n. Okay, these are the locations where you are taking the samples. And the locations, instead of going from minus pi to pi, they are going from 0 to 2 pi. You don't sample 2 pi because that's the same as 0. But we also know that if I know the DFT x of k, from that x of k I can go back to x of n using the inverse DFT formula, 1 over n, k from 0 to n minus 1, x of k, e to the j, 2 pi, k over n times little n. So what we have learned is that n samples of the DTFT are actually enough to uniquely identify your signal, provided your signal was finite duration. It was length less than n. And also, not any n samples will work. In this case, we are taking samples separated by 2 pi over n. Okay? Okay, so this is one aspect of DFT, which is that DFT is just like sampling in the frequency domain, the DTFT, and if the signal is time limited, then you don't lose any information. and you can get back your original signal. And the role of capital N is effectively how many samples you are taking, or how densely or how frequently you are sampling in the frequency domain. So the third point is that the larger capital N is, the denser we are sampling the DTFT, x of e to the j omega. So you are taking more samples of that. It's just analogous to if your sampling frequency increases for time domain signals, then you are taking more samples. Here, if your little n, capital N increases, then you are taking more samples of the DTFT. Okay? And then the values of DTFT are simply preserved in the samples. So if you just look at x of k, there is no scaling of the value. So in the time domain operation, we did see that there was some scaling going on. In the DFT world, x of k is precisely equal to x of e to the j 2 pi k over capital N. Okay. Now, if you go to some texts, you will see that the DFT formula actually is symmetric for both DFT and inverse DFT. What they do is they put a 1 over square root of n here in the DFT formula, and then 1 over square root of n in the inverse DFT formula instead of 1 over n. What it does is it makes the forward and the inverse transform really symmetric. And it has other nice properties. It makes the transform basically orthonormal, which means it preserves the energy and all those other things. The drawback is then this relationship that I drew here doesn't hold. There is a 1 over square root of n factor comes in. So that's why many signal processing texts don't include the 1 over square root of n factor in the forward domain, and instead put the 1 over n in the backward domain. Okay? So just something that you should be aware of. Okay. So the value of then DFT is effectively that it helps us compute or approximate the DTFT. Because in a real world, if I give you a signal, a real world signal is not going to have an analytical form, and you are not going to be able to just calculate its DTFT. The only way for you is approximate it, and DFT is the perfect way of approximating that. So let's look at a couple of examples to see, though, what you should be careful about when you are using DFT to make statements about the frequencies that are present in the original signal. So the first example is x of n equals to 1 for n from 0 up to 4. So you can compute its DTFT. It's x of e to the j omega, that summation n from 0 to 4 e to the minus j omega n. So if you apply the geometric sum formula, what you will get is e to the minus j omega 5 over 1 over minus e to the minus j little omega. And if you do some simplification, what you find out is that it's 5 sine of 5 omega by 2 over sine of little omega by 2 times e to the minus j little omega 5 by 2. Right? This, of course, is a phase shift because our signal is starting at n equal to 0. Right? So this phase shift inside a digital system, no matter where the signal starts, we can say without loss of generality that the signal is starting at n equal to 0. In that case, DTFT will always have this kind of a phase shift. So we are going to ignore that. Let's focus on the magnitude plot. So the magnitude of my DTFT is sine of 5 little omega over 2 over sine of little omega over 2, absolute value, which is like a sinc function. Of course, it can't be a sinc function because DTFT has to be periodic, and a sinc is not a periodic function. So the DTFT for this, I'll go from minus pi to 2 pi. So this is pi and this is 0. Okay, so if you calculate that, you will find out that it's almost, at least in the main period, it looks like a sinc. So, and it's symmetric. It hits maximum at minus pi, at 0, pi, minus pi. Okay, so this value, if you use L'Hopital's rule, you will find out this value is 5. I'm only, again, plotting the magnitude axis. It goes 0 at 2 pi over 5, at 4 pi over 5. So this is little omega axis. Right? And at minus 2 pi over 5, minus 4 pi over 5. Okay. Now, I'm using this example even though you can use, this is just a 5-point sequence, you can compute the DFT yourself. But I want to now relate it to the relationship between DFT and DTFT. So if we want to compute 5-point DFT x of k, then that is simply equal to samples of DTFT every 2 pi over n little omega. So what will be x of 0? So x of 0 is simply going to be, so that will be x of e to the j little omega for omega equal to 0. So this is my value at little omega equal to 0. So my x of 0 is simply 5. Right? Now what is my x of 1? So x of 1 is x of e to the j omega at little omega equal to 2 pi over n. So n is 5 here. So x of 1 is the sample at 2 pi over 5 frequency. What is that value? That's 0. So my x1 is 0. Okay. I can compute it using the DFT formula, but I don't have to. I can just look at the samples of my DTFT. Let's look at x of 2. So that is x of e to the j omega for omega equal to 2 pi by 5 times, now k is 2, so that's 2. So that's 4 pi over 5. That is again equal to 0. So this is my value capital X0. This is my capital X1. This is my capital X2. Okay? Now, here is something that we are not used to. In DTFT, traditionally when we used to plot DTFT, we used to say that focus from minus pi to pi. And we used to only plot from minus pi to pi. Here I have plotted from actually minus pi to 2 pi because DFT starts sampling at 0 and it keeps on going up to 2 pi. It actually, instead of looking at minus pi to pi, it looks at 0 to 2 pi. It still has the same information, right? Because whatever is the information from pi to 2 pi, that is the same as minus pi to 0. Okay? So let's look at what is x of 3. That is x of e to the j little omega for little omega equal to 6 pi by 5. And that is this point. Okay, so this point is 6 pi by 5. And this point is 8 pi by 5. So 6 pi by 5 is also 0. So this is x3. Okay. And finally, x4 is x of e to the j omega for little omega equal to 8 pi by 5. So that is again equal to 0. So this is x4. Okay. So there are two things that are happening. The first is that if I showed you just the DFT plot of this thing, just the DFT plot of this sequence, not the DTFT plot. The DFT plot of this sequence would then look like the following. At 1, I have at k equal to 0, I have 5. At k equal to 1, I am 0, 0, 0, 0. So this is k. 1, 2, 3, 4. If I hide the DTFT plot and only showed you this DFT plot, you actually are unable to make too much inference about the frequencies that are present in the signal, because you took only 5 samples, and other than the first sample, the rest of the samples happened to hit 0. These 5 samples are still preserving the original signal. You can compute the inverse DFT, you will get back the original signal. But these 5 samples, when you look at them, when you visually look at them, they are not giving you enough information. And that is because you took the 5-point DFT. So that's where the role of taking n greater than the length of the signal comes in. Okay? If you ever wondered why should I take a 1000-point DFT of this signal, which is only length 5, here is the reason. Because the longer the length of your DFT, because to compute 1000 points, you have to 0 pad it. Why do I want to waste some space in my computer to add zeros? Because you want to take more samples of your DTFT so that it starts looking like the original sequence that you had. For example, if I just instead of taking 5-point DFT, instead of I did 10-point DFT, then what will happen is that I will now sample here in the middle of samples. I'll sample here, 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 and here. So I'll get these additional samples. I'll have this sample, I'll have this sample, this sample, this sample, and this sample. So now my DFT will start looking more like the same kind of a thing that you expect. And if I made this 10 into 20, then you will even divide these grids even into smaller pieces, and you will take even more samples. It will start looking more and more like the sequence from 0 to 2 pi. Okay. So that's where the length of the DFT comes into the picture, that ideally we want capital N to be reasonably large and that is typically much larger than the length of the signal. The length of the signal. So that we sample DTFT finally enough. Okay. So that when we look at the plot of DFT, we can make some sense of what is happening there. Okay. So if I, for example, took more samples, it will start to look more and more. And then if I were to use, instead of in MATLAB stem plot, I were to use the plot command instead of stem, then of course it will start looking like, even though it's a discrete sequence, right? If I give MATLAB the command to plot, it will connect the pieces and it will start looking like this. So you can say, oh, this is how the DTFT of the signal looked like. Okay. So that's one key point to keep in mind, that DFT samples DTFT, but the longer the length of DFT, the more finely you sample the DTFT, and that is in most cases a good thing, especially if you are doing DFT to understand the frequencies that are present in the signal. Okay? If you are doing it for other reasons, it may not be necessary to increase the length beyond a certain value.
Now, one thing that you want to do when you do DFT analysis is you really want to look at the approximation of the DTFT. So in typical scenarios, if someone asks you, show me the DTFT of the sequence xn that we have defined earlier, then you would expect that person to basically give you a plot from minus pi to pi and have this kind of a plot. Now, if you compare that to what the DFT approximation gives us, right, there are two main challenges associated with using DFT to interpret DTFT. One is that DFT is sampling DTFT from 0 to 2 pi, whereas we really care about frequencies from minus pi to pi. So there is that issue, and then the other issue is that the index, the x-axis index, is just a sequence 0, 1, 2, 3, 4. Right? You want to be able to relate those indices to the frequencies, okay, so that you can label them accordingly. If you were to use MATLAB, you could at least label what these different frequencies are. So in that case, of course, till you are, for k less than or equal to n by 2, the translation of frequencies is very easy. So we know that DFT samples DTFT at frequencies little omega k equal to 2 pi k over capital N, right? So the first part is that for k equal to 0, you know it's omega 0 equal to 0. So you just, if you were to replace this axis, this axis in k by axis in little omega, you know that 0 means 0 radians. Right? Similarly, for k equal to 1, this means omega naught equals 2 pi over n. Right? So in this case, it's 2 pi by 5 or 2 pi by 10, depending upon if I'm taking the samples in between. Right? So if I was doing 10 samples, then it's omega 1. If I'm doing 10 samples, then it's 2 pi by 10 or pi by 5. So then I know that this point is pi by 5 frequency. So I can keep on going that way. I know that k equal to 0, k equal to 2. Again, I'll stick with the 10-point DFT, the one that I've drawn there. So that is omega 2 equal to 2 pi by 5 times 2, that's 4 pi by 5. So I know that this point corresponds to 4 pi, it's 10. So I'm doing 10 points, so it's 4 pi by 10 or 2 pi by 5. So this is 2 pi by 5. And that way, changing the x-axis from the k index, from k equal to 0, 1, 2, 3 up to 9 to little omega axis is trivial. You just replace k by omega k, where little omega k is defined as 2 pi k over n. So going from k to omega is as simple as saying you are given k, you go to 2 pi k over n, where n is the number of points of the DFT that you are computing. So this part is easy. Okay? But this is easy only when we are looking at the frequencies from 0 to 2 pi. Whereas, as I said earlier, you are really interested in looking at an approximation of DTFT from minus pi to pi region. So if I want to actually compute the DTFT approximation from minus pi to pi, what I have to remember is, as we showed earlier, that 0 to pi region, of course, is the 0 to pi region, but the pi to 2 pi region is the same as minus pi to 0 region because of the periodicity of DTFT. So what we really have to do is find out the indices of k that correspond to frequencies above pi, and then we have to shift them manually to come before the indices that correspond to frequencies 0 to pi. So let me repeat that again, that if we want to use DFT to approximate DTFT, we keep the indices k that go up to pi radians frequency, but we shift the remaining indices before the k equal to 0, before the k equal to 0 index. So what I mean by that is exactly this diagram, that what you want to do is you are looking at this plot which goes from pi to 2 pi. If I did not show you the minus pi to 0 plot, right, you just take this pi to 2 pi plot and you will shift it to minus pi to 0 region. Now you don't have the plot, but you have samples of this plot, so you'll shift them from the indices that are above the pi frequency and you will bring them to minus pi to 0 region. So let's identify which of the frequencies, which of the indices go above the pi region, and that's really easy to do, right? Whenever k is bigger than n by 2, so if k is bigger than n by 2, this means that omega k, which is 2 pi k over n, is bigger than pi, right? So any index that is bigger than n by 2, not equal to n by 2, bigger than n by 2, corresponds to a frequency that is bigger than pi, right? So what we want to do is we want to take all indices k bigger than n by 2 to k equal to n minus 1 and effectively just shift them before the k equal to 0 index. So if I were to just give you a DFT plot, which is again the one that I showed you before, so this is k equal to 0, 1, 0, 2, 3, 4, 5, 6, 7, 8, and 9. So this is the 10-point DFT, which comes by taking the DFT of xn equal to 1 for 0 up to n to 5. Right? So in this case, in this 10-point DFT, the k equals to 6 index, so k equal to 5 is precisely equal to pi frequency. So this means what we need to do is we need to take the indices from k equal to 6 to k equal to 9, and we need to put them at the start to give us a better visual representation of what the DFT is from minus pi to pi. Okay? So what you would do is you will take this and instead you will then plot where you have k equal to 0, 1, 2, 3, 4, 5, and then the remaining indices, they will be basically come over here, they have been shifted. So this is effectively the 9 index, and this is the 8 index, whatever is the value there, this is 7 and this is 6. Okay? So this part of the plot is effectively moved from the right side of your plot to the left side of the plot. And the reason for that is because now if you were to take more and more and more samples, this is really looking like the DTFT from minus pi to pi region. Okay. Now, of course, you can do this process manually, but if you were to do it in MATLAB, actually MATLAB provides you a very nice function. So if you want to do this process in MATLAB it is called FFT shift. You use that, you give it a sequence, and it automatically takes all the indices that are above n by 2 and shift them to the front of the sequence. Okay. So you don't have to manually do it, but you need to know why we are doing it. We are doing it because we really want to visualize or relate the minus pi to pi frequencies. Okay. So that is one aspect. But where I have now shifted these frequencies, I have to be now careful about the other part. We started by saying, well, it is easy to map the indices to frequencies. But now you have shifted the indices from k greater than n by 2 to n minus 1 to the left. So now you can't use the same relationship. Right? So what is the relationship that, of course, for these indices, the relationship stays the same because you have not shifted them. So if you want to write the frequencies for these indices, the relationship is still the same. This is omega equal to 0. This is omega equal to pi by 5, and so forth. But what about these values now? You have shifted them. Well, that again just follows from the periodicity of the DTFT. So let's focus on k equal to 9. Right? In the original case, when I did not do the shift, k equal to 9 corresponded to omega 9 equal to 2 pi by 10 times 9. That's 9 pi by 5. Okay. But now you are interested in a frequency which is between minus pi and 0. So this, of course, 9 pi by 5 is of course bigger than pi. This is not in the principal range of minus pi to pi. But if I want to ask what is that frequency in minus pi to pi region, we know how to do that. So if you want to now compute when I have shifted what is the effective frequency, all I have to do, because of the periodicity, it is in the next interval. It's from now pi to 2 pi. If I want to bring it from minus pi to 0, all I do is I subtract 2 pi from it. Well, that is going to be equal to minus pi by 5. Which is to be expected because the gap between any two DFT samples is 2 pi by n for an n-point DFT, right? So you look at it visually, and 9 is now only one gap away from 0, but on the left. So if 0 corresponds to 0 frequency, then the index to the left corresponds to 0 minus that gap, so which is minus pi by 5. I can do the same trick for k equal to 8. So originally k equal to 8 is 16 pi by 10 or 8 pi by 5, which is greater than pi. I have moved it to the left. So to compute the value now that corresponds to minus pi to 0, I'll subtract 2 pi from it, and I get minus 2 pi by 5. So that way you can actually label all of these frequencies. So this will be minus pi by 5, this will be minus 2 pi by 5, minus 3 pi by 5, minus 4 pi by 5. Okay. So when you do FFT shift, you have to then be a little bit careful about the labeling of the x-axis. Okay.